Alright, here's a video of us implementing the elastic heuristic planner. So here we have the simulator running on this side, and hooked up to our simulator, so of course the matrix itself. And on this side we have the simulator running on one of the onboard computers. And this is how we plan on performing obstacle avoidance. Basically we have laser scans, which we have both point clouds and laser scans. Let me just show you what they look like. They won't make much sense on the map just because the machine's currently sitting still behind me and not actually flying through a virtual environment. So those are the point clouds. And more useful for localization, which we do use AMCL, is these laser. So here you can see the outline of my living room. And these are just laser points that are basically extracted from the point cloud. And this allows them to be used with other packages such as AMCL or even G-mapping if we want to create maps. And using lasers is there are packages that use point clouds, but unfortunately, given the limited processing space and the fact that we probably don't need to map 3D maps, a 2D map will do the job. And this will be great for localization inside of a building, and that way we can ensure that our matrix has no problem finding its way back out through the door. So those are the sensors that we'll be using mainly for obstacle detection. Off and go back to the navigation simulator. Alright, so here we're back at the simulation. So there's currently two methods we implement on navigation. So the default ROS stack uses what they call move base, which are velocity commands. But as you can see, there's these lines that are generated for trajectory. We can actually use those lines for navigation as well. So instead of using velocity, we can use waypoints. So you notice there's two lines. So there's actually a local trajectory and a global trajectory. The global trajectory has this much slower update, so it's not as useful for obstacle avoidance, or something that dynamically is generated. So for obstacle avoidance, we probably want to stick with using if we want to use waypoints on the trajectory, we probably want to stick with the local trajectory. And that one is up, I think we have this set updating at 20 Hertz. So just a quick demonstration of see if we can make it all the way there. And just to show you that we have, it's actually being run on a simulator right here. There it goes. So the red line is the local, and the white box around it is also the local cost map, and that's the cost map that's mainly used for generating updates for obstacles. So here in this demonstration, I believe we're using the velocity commands and they work pretty well, mainly because they are kind of slow. Let's take a look. Yeah, it's barely approaching. So if you add those two angles up, it's still under 1 meter per second. Look. So there's still quite a few things we need to adjust with the parameters to make sure it works correctly. And we also have to test on the actual aircraft. Unfortunately, we can't, we'll do testing a little later just because we had a few accidents, but that's not a big deal. We've done velocity-based commands before and they're pretty stable. And at speeds of only 1 meter per second, less than 1 meter per second, I don't expect anything to go wrong. Should be a pretty straightforward test. And there you go. It navigated from all the way this room to that room. So in the real world, we actually won't but what we'll do is in this white square, the local square, it will dynamically generate obstacles based on the laser scanners. And you can, as I've shown you before, we have a near 360 detection of laser scanners and the guidance sensors. There are 30-degree dead spots on each corner though, so there you have it. The simulation of our matrix flying through a maze, and which also has inherent abilities to dodge